Hey, hi, I'm Maria or Majo. I'm a grad student in physics at UT Austin, and uh, I study black holes and galaxies in the daytime. So I'm gonna talk to you guys about uh, how space actually can make sounds and how that makes any sense and how that came to be. Okay, so I'll start. I mean, all of us tend to think of space just as the distance between objects, some sort of like inert canvas, in which we like draw objects. We just, yeah, it's just the scenario in which things are. We don't think of it as a dynamical entity, like something that, by that I mean something that has energy or something that could change the distance between objects without the objects moving themselves. But that is actually not the case. Space is something that changes, it evolves, and in some cases it does so at a frequency that we can hear. And this talk is about those cases. So for this talk, because I do have some audios, I will ask you please to find a quiet, dark room. There's some nice animations and yeah, some good audios. Maybe like just get a good headset and just get comfortable. Yeah, if you do not, yeah, you might have to make sure that your sound is good to be able to hear some of the stuff that I'm about to show you. So that's just a disclaimer. Hope that was the 30 seconds worked for getting you there. Okay. So that chirping sound that you're hearing now, that is the sound of black holes colliding. They're sounds from the past, and they're measured in the last 5 years, but they were emitted many, many millions of years ago. It is the sound of space itself contracting and expanding as it's carried by space alone. Just by space. Us. Yeah. So the first time that humanity witnessed and recorded the collision of two black holes was 5 years ago. Had we been near enough, we would have actually had no trouble hearing or seeing that collision. But it has actually required incredible feats of engineering and good knowledge of what the sound would be like to detect them. So, but yeah, had we been near, not only would we have heard them, but our state-of-art modeling tell us that they would have looked just like this. So yeah, that's not like an artistic rendition of what they would look like. That's actually how you would have seen them if the background had just been a bunch of stars. So I'm going to play that again one more time because it's really cool. Okay. So yay, hooray to engineers. We have actually detected, the sound of space, gravitational waves. But what does that really mean? How do we even how can we even start like understanding what that means? Like wrapping our head around that. Okay, so in order to figure that out, we will have to understand some things actually about the source of these waves, this, changing of space and the sound, and that would be black holes. And we will have to understand black holes first statically and then in movement. So yeah, black holes. First, why are they black? And second, kind of like, how can we hear them, right? So I'll start with why are they black? And in order to answer that question, yes, I will take you back to high school and talk about Newton's gravitational force. So everything, basically, what you gotta want to get out of that is everything that has a mass is attracted to anything else that has a mass, and it is attracted in such a way that the bigger the mass, the more the attraction, and the bigger the distance, the lesser the attraction. Now, anything that has a mass obviously is subject to this. Like that would be, for instance, missiles that are like shot from the Earth and just get trapped by that gravitational potential, or like, yeah, they can orbit around the Earth if they get enough velocity, or if you actually throw something with enough velocity, you can basically escape the gravitational attraction, like to all effects. Now, as I said, it's not just about things being attracted or fallen into the Earth. Is about like planets, or like the Earth falling or being attracted into the sun. Is about the sun falling into the big black hole at the center of the Milky Way, Sagittarius A, a million times heavier than the sun itself. And it's also about and that black hole itself is also just like falling into another black hole at the center of the Virgo cluster, like M87. So everything is affected this way. Now, that leads us to think, like, I mean, maybe that's just the key, right? Like maybe even light itself could be just like bent by the gravitational, by the mass of this black hole, and just get trapped, and that's why they're black. But there is a problem with that, and that is basically that light is not massive, right? And that law that I just stated, it only is about things attracting each other if they have mass. So in order to fully understand why black holes are blacks, we would have to upgrade our understanding to Einstein's relativity theory, which you might not have talked about in high school. Maybe you have. I don't know what they teach now. Anyway, so energy, what Einstein said is that energy, be it in the form of mass or movement, deforms the space around it. So that means everything within space, light included, should feel this deformation. If you think of space as this like, sheet on which massive objects are just like, kind of like laying on, so they deform it. That's more or less what they would look like, right? Like the bigger, you can think of space like that. The bigger an object, the more massive an object, the more it will deform space around it. And perhaps even a better way to look at this than a sheet, might be somewhat deceiving, is a grid. So if you have an object, this is a little object moving around space, and this is what it's doing to the space around it, kind of like compressing it, curving it around it. So great, now we know that mass and energy curve space, but that doesn't actually tell us how objects move within that curved space. And luckily for us, Einstein also figured that out. So it's basically what he figured also, and one of the postulates of his theory is that objects are lazy. They cover the least distance possible between point A and point B. And we normally, in technical terms, call that a geodesic. To be a bit more clear about what that means, so, if in a map, the shortest distance between New York and Madrid would just be a straight line. But you might, that's, but the Earth is a curved space, it's a deformed space, so to speak. So this is actually a perfect example to show you what, like the concept of a geodesic. So if you're used to travel long distances, you might have noticed that a plane took weird paths on the map. It didn't go in a straight line from New York to Madrid. It kind of like went like this. And the thing is, this plane was just following a geodesic. This plane, instead of going like this, which is actually longer, went like this in a great circle. And the shortest path on a curved surface on the Earth, just as on space-time around black holes, would be a geodesic. So yes, so your pilot probably did not did not do this because he was following the laws of nature, or it's more like the laws of economy, but it was the same principle. Now, photon, likewise, if you have a photon traveling near a black hole, it will do so also along a geodesic. Traveling in a straight line would mean covering a longer distance, but curving inwards and being sucked into the black hole. So the space around a black hole is so curved that if you are too close to black holes, the shortest path is always into the center of a black hole. And this is why black holes are black, and this is how gravity works, at least statically, right? But I did promise that I would tell you how is it that space can make sounds. And so let's go back and actually talk about the first time that we heard any sound from space. So the first time that we ever heard black holes colliding was in the morning of September 14th, 2015. It was the sound of two black holes that were about 30 times the mass of the sun, and they had been orbiting around each other for millions of years. As they got closer to each other, they moved faster and faster until they finally collided and merged into a single black hole. A fraction of a second before they collapsed, they sent a vibration across the universe at the speed of light. And on Earth, billions of years later, a detector called the Laser Interferometer Gravitational Wave Observatory, LIGO, picked it up. And this is what those waves, when I say gravitational waves, what I mean is something that looks kind of like this, at least pictorially like this. So gravitational wave moves out from what caused them, like ripples on a pond, and they get smaller as they go further from their source. This is a schematic picture of what gravitational waves do. You see this fair similarity. These are both schematic pictures, and reality is actually a little bit more complex. So this is a little animation that is a bit more closer to the true of what, like the fluctuations in space and would look like as two black holes merge into each other. Perhaps to actually understand, again, like as a part of answering this question, I will ask another question, which is, what would it feel like if waves passed through you? And it would really just feel like gelatin, like jello. As if you're standing in front of the wave, you would feel, if your body was sensitive enough or the wave was sufficiently strong, you would feel a compression in this direction, and a stretch. And at the same time you're feeling this compression, you would feel a stretching in this direction, and then you would feel a compression in this direction, and at the same time a stretching in this direction, and so on and so forth as the wave comes and hits you. But we don't feel that, right? Like, we actually don't feel that. And the reason is, this is a very tiny effect. It is so tiny that if you imagine a 4-kilometer long arm, like a huge, like imagine that you yourself are 4 kilometers long, what you would feel would be something, a variation so small that that thing moving was kind of like a pictorial electron. This is a proton, and this 1,000th of the diameter of the proton would be what you would feel if you were a person that is 4 kilometers long. At least that is for the objects, for the black holes that we've detected so far. So lucky for us, we actually do have these things, right? We have we have 3 detectors that are working right now. We have LIGO, as I mentioned, the Laser Interferometer Gravitational Wave Observatory. It consists of 2 detectors, one in Washington and the other one in Livingston, Louisiana. Hanford, Washington, and Livingston, Louisiana. And it works in collaboration with Virgo. in Cassina, Italy. So these three guys, all of them with 4-kilometer long arms, are detecting gravitational waves and are measuring motions that small. They are currently not detecting gravitational waves because it so happens that those three places are one of the most hit places in terms of the corona. So yeah, but there's no correlation between coronavirus and gravitational waves, though, as far as anybody can tell. Anyway, if you're interested in, so how does those arms, okay, so that's really cool, you know, like we have some L-shaped instrument that has 4-kilometer long arms, but how does it actually work, right? So I'm going to show you a video maybe a couple of times to explain it. We have, and I'm going to stop it now. So these 4-kilometer arm legs, they have a laser that shoots into a beam splitter at where the legs join, and that beam splitter lets some light pass through. Whoop, sorry. It lets some light pass through, and it reflects some light. And that reflected light bounces back off another mirror and comes back into the beam splitter, the same way for each arm. When a gravitational wave passes, it stretches and compresses the length of the arms in such a way that before, if it was static, you know, it would not interfere with itself constructively. It would just destroy the light, you know, as it passes. But because it is moving, it interferes with itself constructively and destructively as the gravitational wave stretches and compresses the length of the arms. And that is basically what we measure, this little thing here, you know, the intensity of the light on that end. Good. So in a sense, these detectors that we have, they're kind of like radios, right? Radio waves are passing through you all the time. And you can't only hear them if you have the right kind of detector, a radio. And you can't really easily tell where they're coming from, just like with these guys. So it not only, as I said, not only is it like, you know, like a radio in that sense, but actually, unlike radios, if you were near enough a binary black hole system, perhaps about a solar system away, for the ones that we have heard, you wouldn't need anything but your ears to hear them. You know how sound is actually pressure waves carried by air, but in this case, the cavity within your ear would stretch and compress in such a way that you would hear the gravitational wave without the need of air. Now, I talked about the first detection, but I didn't actually, you know, let you guys hear it carefully. So I'm going to play it for you guys because it was a big step, actually, I think, in the history of science. And, so I'm going to play it first as it was originally heard in the frequency that it came. And then I'm going to raise the frequency a little bit so it's like easier to hear. Yeah. That is what we heard. Then that was our first detection, which I've talked about already. But that is not the only detection that we've had. We actually, at around like 2019, released our first catalog for gravitational waves, and we had like at least 10 black holes out there, and yeah, one neutron star. And it was a big effort with like at least 1,000 people, if not more, and it's even bigger now. We here at UT are actually part of that effort. That's our group. That's me. This is my advisor, and this is a bunch of hooligans that we work with. So anyway, what's coming? We have a 5 detector network, actually. So we're not only going to work with these guys, over here. But before Corona, LIGO India was already getting into the picture, and this guy is still taking data up in Germany. And Kagra, is also a part of our network. So we're gonna get better resolution, but we're gonna get better accuracy and better signals in general. Yeah. But not only that, we also have plans for new detectors. Some of them are much closer in the future, like Lisa, and some of them are not so, where they're still like prospects and are unclear. So Lisa would be the same idea, a laser interferometer, but it would be in space, and it would be targeting very different kind of masses of black holes, and also like gravitational waves from the beginning of the universe. The Einstein telescope and the Cosmic Explorer are basically the same thing as LIGO or Virgo, but like bigger, better. This one is a European effort, and this will be a United States effort if it does launch. This one is probably much I think there's like a higher chance of this one launching. I'm not sure about this one. If it does launch, it would be really cool. It's like 40 kilometers long arms, and they are so long that the curvature of the Earth is actually a factor there. So they would have to be like under the Earth in some places. Good. So that was it. I think I'm within time. The future is bright and noisy. Before leaving you guys, I wanted to make a slight, a small disclaimer. So what I do normally during the day is study black holes and well, galaxies. But especially since Corona, me and a group of friends at UT have been trying to figure out ways in which we can help. And I think one of my friends is posting now in the chat about how we are 3D printing face shields for healthcare workers here at Austin. So if you want to help us 3D print face shields, and please check that link. And that's about it. Thank you for hearing me.
Right, and thank you, Maria. That was amazing. So now we're going to take some questions for you. And we've got a couple, but I had one for you first. Oh, there I am. Jacob, you don't need to put me on just to talk. We can leave the camera on. So my question was, can you clarify how LIGO detects these tiny gravitational waves, and how does it filter out earthquakes and trains and normal things that shake the Earth that they sit on?
Right. So we actually have a lot of effort involved in understanding our noise. One of the easier ways to notice if something is noise or not is to correlate the signals between the different detectors. If something that looks like a gravitational wave was heard by the 3 detectors at basically the same time or close to the same time, then it's very likely to be a gravitational wave. We also have seismometers and many other noise detection instruments that are also running in parallel at the same time, so we can notice if those were triggered, maybe there's a good chance that event is not good. We do a lot of post-processing after the fact just to make sure that is a true gravitational wave event.
That makes sense. A lot of data to process.
Yeah.
We have a couple of questions on the feed. So how will hearing black holes make a difference to us humans?
Well, I mean,
that's a why do you science?
Exactly, right? I think this question was asked to Feynman once. And I think his answer was, I, science is like sex. Sure, there's some practical reasons for why you would do it, but that's not really why you do it. But really, though, this is an amazing feat of engineering, right? If you're thinking in practical terms, being able to achieve this has like vastly improved, like what we can do engineering wise as well. Like experiments like this or CERN have like been like have helped us in part like get something like the internet working, right? Like CERN was a big player in the development of the internet.
Mhm.
So it's not clear how science helps humanity directly but it's clear that it does help. I mean, aside from just curiosity and understanding our place in the universe, but it does help us indirectly in terms of technology. That's what I would say.
So then it's up to the engineers to actually do something with the science.
Yeah.
So, okay, I have this ongoing engineer versus scientists debate with Lewis, the founder. Um, so another question: uh, when you say the sound of space,
Uh-huh.
which is gravitational waves, is that sound the same as the sound that we think of on Earth, or is there a difference?
No, no, there's a difference because this is so the sound that you hear on Earth is because there's compression waves on the air molecules that are hitting your eardrum. So you're getting like this like pressure coming in and like hitting your eardrum, and that your brain is activated into sound, and it's doing it at a certain frequency, like around 200 decibels, or near that. uh, Gravitational waves would compress and expand the space itself, not things within space, but space itself. And they do so at that frequency as well, at audible human frequencies.
That is a fundamental difference. Thanks for explaining that.
Hmm.
Um, so, are there any detectors planned in the southern hemisphere?
No, but that would be great. But no. Yeah.
Are there any big research universities or anything that might step up for that? Or
Um. Well, perhaps. Um. I would imagine research universities in the southern, like maybe I know a big part of the collaboration is Australia.
Hmm.
Australia has a big group, so I mean they're working with
They've always
us.
helped with
Yeah,
the space program.
right. Not just with the space program, right? Like so, all of these experiments are not just like from one country; they're international, but they're placed in specific countries. There's no plans. This placement is based also on who put more money and stuff like that. But I mean, there's still a lot of players from all over the world.
Gotcha. All right,
Yeah.
one more question. Um, and that is, and I'm paraphrasing a couple of questions here, but what other than colliding black holes can the laser interferometer possibly detect?
Oh, okay. So that's a pretty good question. So this laser interferometer can detect black holes. It can detect neutron stars merging. So it can detect black holes merging, neutron stars merging, and neutron stars black holes merging. Aside from a lot of noise. So for astrophysical sources, those are basically the ones that we can detect. What is a neutron star? A neutron star is the most compact star that we know of. You know, so if it were even more compact, it would immediately become a black hole. So that is the kind of black holes that we can detect. Now that is just for this interferometer, the one that we have on Earth. LISA is a whole other story. LISA is the one that will be floating in space. That one, which is supposed to be launched within like 10 years or so, that one will be able to detect waves, gravitational waves from the beginning of the universe.
Wow.
And big black holes, like, you know, a very different sort of mass range in black holes and white dwarfs, also, which are like are another kind of star but less massive and are closer to us, and we already detect them in other ways. So that one, it has a beautiful case science, and it's worth a whole other talk on its own.
Great.
Yes.
Well, we will definitely have you back at Nerd Night to talk about that in the future.
Yeah, I'd love to.
Maria, thank you so much. Fascinating talk. And just imagine all the applause you'd be getting if we were at the North Star.
Thank you.